The second part of this lecture. In the first part, what we did, we saw how to find local minimum, local maximum of a given function, correct? And we saw the second derivative test also, okay? And we had defined what is the notion of absolute maximum and absolute minimum there at itself. So in this part, we are basically just going to discuss the idea of finding absolute or the global maximum minimum, okay, for a given function. I did not do this in the first part because the two ideas require slightly different thinking, okay, and this result we could have talked about in the first part itself, but I just did not because it could have added some confusion, okay. So okay, the situation is this. Basically it says that, when we are talking about maximum or minimum values, okay, there should be some guarantee that that they exist, okay. So for some functions we should be able to talk, or we should be able to a priori know that maximum or minimum will exist, okay. So this is what this extreme value theorem tells us. It says that you start with a continuous function, okay. So this is important. You take a continuous function which is defined on a closed and bounded set, okay. So imagine the situation for single variable also. You had a similar setup, you had a similar result over there also. So I have a continuous function of two variables on a domain which is a closed set and a bounded set, okay. So these two terms you are familiar with. Then what one can guarantee, that f attains its absolute maximum as well as minimum on this set, okay. So what does it mean when I say attains? It says that there are going to be 2 points in the domain, okay, x1 comma y1, x2 comma y2, such that this is absolute minimum and this is absolute maximum, okay, and these 2 points are in your domain. This is important. This is the meaning of attains, okay. So this happens when you are working with continuous functions on a closed and bounded set, okay. So this is important here. All the three terms are important, okay. So if you just go back to your calculus 1 course, look at the similar result and think of dropping one of these conditions and see that this result is not going to be true, okay. And exactly the same functions which give you counter examples there will help you there in this situation also, okay. And okay, so this is second part of this statement. It says that you have absolute maximum and absolute minimum, okay, and this is happening that this absolute maximum and minimum, they will occur at a critical point of f in the domain or at a point on the boundary of A, okay. So these absolute maximum or absolute minimum will either occur at a point which is a critical point inside the domain, okay, or it's going to be on the boundary, okay. So when I have a function or when I have a set sitting inside R2 or in R3, I can talk of its boundary, okay. So for very simple sets like rectangles or disk, those kind of sets we are going to look at, and we will see that we can talk of the boundary, okay. If you have not seen the definition of boundary, okay, let me just recall the definition of boundary. So first of all, we define what is a boundary point, okay. So you take a point in R2 and take a set A, okay, non-empty set of course. So you see that here I am writing x comma y is in R2, so I am not starting with the point coming from A, okay. What I have a set A and you take any point. So we say that this point is a boundary point of the set if every disk centered at this point, okay. So no matter how small or how big disk I take around this point, this disk has to intersect with the set A and its complement both, okay. So this is a point so that any disk around it has some part of A and also has some part of its complement. So this is by the boundary, correct. it is not in the interior of A, or it's in complement. Okay, so such a point is called a boundary point, and when you collect all the boundary points of a set, that is called the boundary of A. Okay, and often this is denoted by this partial A, del A. Okay, so this is the complete definition or complete result. Okay, so what there are three things: that absolute minima, absolute maxima is guaranteed to exist for a continuous function on a closed and bounded domain. Okay, and not only that, they will occur at a critical point or at a boundary point. Okay, so these are the three things. So when I now about the proof of this result, you can actually do it yourself. Okay, so try to just write down the proof. This is absolutely fine, and it's very simple. Okay, in fact, if this kind of question comes in the quiz, don't be surprised. Okay, all right. So just to summarize, because this theorem will tell us that in order to find absolute maximum and absolute minimum on these kind of domains which are closed and bounded, we need these three steps. Okay, first you compute all the critical points of the f in the domain and find the extreme values. Okay, this could be minima or maxima, and then find the extreme values of f on the boundary. So that means you have to first find the boundary and then find the the maximum and minimum values, and then because these are the two possibilities where maxima and minima will exist, so you have to basically compare the values which are obtained in step 1 and step 2. So the largest of the value is going to give you absolute maximum, and then the smallest is going to give you the. So there are three steps: first compute critical points, and then the extreme values, and then compute the boundary, and then compute the extreme values. Okay, so this can be slightly lengthy in terms of computations, but idea is very straightforward. Okay, so I will illustrate this through an example so that you are comfortable doing other examples, and you know what exactly we are doing. Okay, so for example, I take this function. Okay, it's not so easy a function because it has got three terms. There is a mixed term also. So and the domain is a rectangle. Okay, so here you see this is less than equal to less than equal to. So one can easily check that this domain where x and y are varying from -1 to 1, including minus and 1, this is a closed and bounded domain. Okay, and f is just a polynomial in x and y, so this is definitely a nice function. It's a continuous function. So in order to find absolute maximum or absolute minimum for such a functions where the domain is closed and bounded thing, that means it has got a boundary also, and I know that absolute maxima and minima is guaranteed because of our extreme value theorem. So we need to go through these three steps. Okay, first we are going to analyze the critical points, so find them. So to find the critical points, you have to first compute the partial derivatives. So do that. So this is a computation of partial derivatives gives me these two equations. Okay, when I set them to 0. Okay, so as in the previous case, from 1 for example, from here you can substitute y equals to x square by 4 in this equation, and you precisely get this. Okay, so the solution of this is going to give you the three possibilities for x. X is either 0 or x square is equals to 2, which is plus minus square root of 2, isn't it? But immediately you should not jump. You also have to be careful that what domain you are working with. Okay, so x equal to 0 is certainly inside this, but these points, square root of 2 is bigger than 1. Similarly, square root with a negative sign, correct? This is less than -1. So these values of x, they are outside the domain, so we are not going to consider them. Agreed? Because this is not inside my domain. So when I try to find the critical point, because this function is actually defined everywhere, but I am only interested in this domain, this part of the domain. So even though it has got more critical points, but we have to be careful. We need to worry about the critical points only inside the domain that is given. Okay, so we will not consider these critical points which are corresponding to the square root of 2 values. Okay, and the minus. So as I said, we will only worry about the critical point 0, 0. Okay, so at the critical point 0, 0 the value is 4. Okay, so we put it. Now this is the first step. We found the critical points and then we have the extreme values. Okay, and second one involves finding the boundary first. Okay, now this was a rectangle, actually it is a square here because x and y, they are having the same length intervals. So the boundary is going to be these 4 lines, correct? Because if I take a point here on this line and take a disk, so it is going to be around any disk around this will have some part of the rectangle as well as outside the rectangle, correct? So, and this is true for any point on these 4 lines. Okay, so the boundary consists of these 4 sides of the rectangle. Okay, if you want to use the term square, that is better. Okay, so okay, now we have to analyze the function on all these 4 sides. Okay, in the interior part the critical point was 0, 0, at which we have already found the value, correct? So now let us try to analyze all these 4 lines. Okay, so separately you have to do them. So I have written right side, so this is right side is x is constant 1. Okay, so that is what this is. So x is constant 1 and y is varying from -1 to 1. Okay, so what we need to find out the extreme values of function on this side, correct? So if I do that, I put x equal to 1, what I get, I don't get a value, I get a function of y. Okay, because there were terms in y. So this basically tells us that you have to now analyze this function. But good thing here that this function, because we have put x equal to constant. Okay, so this is just a function of single variable. Okay, so we can apply single variable theory. Okay, so give it a name, call it g, and now we need to figure out whether this function has some extreme values on when y is varying from -1 to 1. Okay, so in order to do that, again you have to find critical points. Okay, but now these critical points are for the function g. So when you are finding the critical points, that means you look at the derivative of g, put it equal to 0, and it is going to tell you that y equal to 4 is a critical point. So at y equal to 4, you evaluate your function, which is same as f of 1 comma 1 by 4, and the value is 19 over 4. Okay, so there was only one possibility, the critical point is only 1 for this y, and at that point you have this extreme value. Okay, all right. Now again the similar situation which we are actually discussing in the context of 2 variables, you had in 1 variable also. If I had a closed and bounded interval, so to find the extreme value, what we had to do, you had to do it at the critical point and the boundary points, correct? So we had to also worry about the boundary points. So for boundary points of this variable y, they are -1 and 1, correct? So evaluate your function at -1 and 1 as well. So this is going to give you another 2 values possibly. Okay, so f of -1, sorry, g of -1 is same as f of 1 because x equal to 1 is fixed, and g of 1 is equal to f of 1 1, and you get these 2 values. Okay, so you see you are going to get different values over here. Okay, so this is only one side. Now we go to the other side. Let's say the left side. So left side has x equal to -1 now, and y is again the same, but because our function is symmetric with respect to x or -x, so I am actually in this case I am just going to get the same function g, but this may not happen all the time. Your function, it depends on the function. So in order to analyze the same thing, we don't have to repeat that, and we get exactly the 3 values even in this case. So the left and right sides can be handled together in a way. Okay, now the remaining 2 sides, the upper side is y equal to 1 and the lower side is y equal to -1. Okay, so let us look at that. So if I set y equal to 1, I am going to get another function here, and that function is 8 minus x square. Okay, so in the expression of f, you set y equal to 1, so that is going to give you a function of x. So and then what you do, now you need to analyze the behavior of this h as a function of single variable. So you look at its derivative and then equate it to 0, find the critical point which is just 0 over here, and find the extreme value at that critical point. So that is h0 is f0 and by equal to 1, so f0 comma 1, and this value is 8. Okay, and this is at the critical point. Now you have to look at the boundary points for the function h. So boundary points are again 1 and minus 1, so again you compute them. Okay, so this is a process which you have to keep on doing, and similarly you go for the other boundary, which is the lower boundary, and by equal to minus 1. So notice here that the upper and lower, because there was no symmetry in by and minus y, so this is a different function when I said by equal to minus 1. Okay, I get this function, so you have to analyze it separately. Okay, so when you analyze it separately, the same idea, find the derivative, equate it to 0, find the critical point. So this is a 6x equal to 0, so that means x equals to 0, so the critical point is x equal to 0, and find the value of your function at that point, which is this. Okay, and then look at the boundary points. The boundary points are again minus 1 and 1, and you get these three values. Okay, now we have completed two steps. The first step was to find the critical points of the function in the domain, and step 2 was to find the extreme values on the boundary. Okay, and the third step is basically you compare. So third step will tell you that the value at the critical point happens to be the minimum, so it is an absolute minimum, and then value at the boundary at 2 points we are getting this maximum, this 1 and minus 1 and minus 1 and 1, so this is the absolute maximum. Okay, so this is a process. You have to be careful that when I am talking about domains which are closed and bounded, and then for continuous functions the extreme values are guaranteed, so they will occur either at a critical point or on the boundary points. Okay, so you have to analyze the boundaries separately. Okay, the test does not apply there. So because rectangle is such a nice thing, but if I take some other like a disk, there I won't be able to set x equal to constant. Okay, there it will be x square plus y square something is equal to a constant. So it will depend on the function you are working with, and as well as on the domain you are working with. Okay, so solve a lot of examples of this type, and different examples will require different kind of analysis. Okay, but the idea should be clear. Okay, so I will stop here, and I will have one small video, one small lecture again for this week, because next week we are going to have recess. So if I discontinue it, we will have to start all over again. So I will just have one extra lecture. It's not really an extra lecture in terms of total hours. If you see, it's not really extra, but I just want to complete this section, so that so I will have another small lecture, very small lecture. Okay, see you.